There we go. I think we're started now, so can everybody on Zoom hear me okay? If you're on Zoom, just give a thumbs up reaction to make sure that everything's working okay now. Excellent. Thank you very much for that. Just a short introduction. So my name is Jamie Gillespie for the Security Working Group. We have presentations for this session that we'll carry through. I believe that it's just going to be this presentation and we're not continuing after the break. Yeah, so just looking at the co-chairs that we have here, Yoshiaki, Rakesh, and Sankar providing support for the Security Working Group. Today we have presentations. We have 3 presentations that are going to be given. Do we have Taif connected at the moment? And then the other presentation, Abdullah Ahmad Omar Bahashwan. So we can hand over for presentation to you. This presentation on the high and low rate data sets for DDoS attacks against SDN networks.
Very good day to everyone. I'm Taif Al-Alamiti from University Science Familia. So my research title, as Victor said, is towards a lightweight detection system leveraging mapping technique with Brava feature selection algorithm for selective forwarding attack with local and noisy network of Internet of Things. So first of all, Internet of Things is referred to a collective network of connected devices. This technique facilitates the communication between the physical devices and the digital worlds. So the Internet of Things technology create this communication between the devices and enable them to connect to each other in a network. As we know nowadays, this technology is widely separated in different applications. For example, we have Apple ecosystem and Huawei ecosystem. This is an example of a small network of Internet of Things. To continue, we have a technique here which is called the local and loosey network, which is considered the backbone of IoT network. In this network, the Internet of Things sensors are organized in a form called local and loosey network. So the integration of local and loosey network with the Internet of Things enable the IoT to facilitate in a wide difference diverse types of sensors across a wide array of IoT applications. So the security here is crucial. Why is crucial? Because these types of networks are extended to vital infrastructure, area of privacy and sensitive industrial process. So the security of local and loosey network has become one of the most heavily studied researchers in the recent period, and it addresses a wide range of research initiatives. So as I said, the local and loosey network is vulnerable to a wide range of attacks, and these attacks can be internal attacks when the attacker node be a part of a network, or it can be exposed to external attack when the attacker node is outside of a network. Here we can see in this slide, RPL attacks can be classified into 3 attacks. I would like to mention here that the local and loosey network have different types of protocols, and RPL is one of the most popular routing protocols in this types of networks. And this protocol is vulnerable to different types of attacks. As you can see here, there is 3 main types: resource-based attacks, topology-based attacks, and traffic-based attack. And in abstract explanation, the resource-based attack, when the attacker attacks the resources of a network by sending a huge types of packets to the network. But in the topology attack, the attacker exposes the targeting the topology of the network, trying to destroy the topology of a network and then break down the network. And the last type is traffic-based attacks. Here the attacker aims to expose the network and try to steal some critical information from the network. Okay? So in this research we focus on detecting one of the most popular topology-based attack, which is the selective forwarding attack. Here, this figure shows the current direction in RPL protocol. As you can see here in the slides, the current research direction of the RPL can be classified into 2 types: RPL security and non-RPL security. I think this slide is very most important for the researchers, who are working in this field. So in this research, we're focusing on the API security and specifically the intrusion detection system. In addition, the intrusion detection system can be classified into subtypes, which is hybrid-based approach, signature-based approach, and anomaly-based approach. And in this research, we study the anomaly-based approach, which is have several types: machine learning, deep learning, and hybrid approaches. So we have also another technique which is called the feature selection. Feature selection is one of the most popular techniques for dimensional reduction and improve the performance of intrusion detection system. So these techniques can be classified into three main types, which is called the filter method, wrapper method, and embedded method. So basically the filter method try to rank a group of features or make the evaluation based on mathematical expression. For example, one of the most important algorithm in these types is called the information gain, the mutual information, the entropy algorithm, and then the set of features will be evaluated using the machine learning algorithm. The second type, which is called the wrapper method, is types of algorithms like the recursive feature selection, the meta-heuristic algorithm. These types is evaluate a subset of features, then using machine learning algorithm. Then this process will be repeated until get the optimal set of features. And the last type, which we have the embedded method, which is a combination between the filter method and the wrapper method. So, as I said, the meta-heuristic algorithm is one of the most popular wrapper feature selection technique. So meta-heuristic algorithm has been widely used to solve different real-world complex problems. So as we can see here, there's different types of meta-heuristic algorithm. There's evolutionary algorithm, physical algorithm, nature algorithm, swarm-based algorithm, and biological algorithm. So these types is used to solve different types of problems. And in this research, we used the particle swarm optimization, which is one of the most popular swarm-based algorithm. So selection for this algorithm is one of the most known algorithms and have a fast execution time and a few control parameters. And we used in this research for feature selection algorithm. So what we have been doing in this research, as you can see here in the figure, that the existing solution, the meta-heuristic algorithm, rely on the machine learning algorithm to evaluate a subset of features. So basically, we have a full set of features inserted to the meta-heuristic algorithm. Then the meta-heuristic algorithm, as you can see here in the left figure, the start agent start to generate the candidate solution. After that, it will input to the evaluation function, which is here we have the machine learning algorithm. So this process took a huge training time. Why is that? Because machine learning want to make the training model and production model, and this process is iteratively repeated and take a long execution time. So what we propose in this research, we use a new fitness function or evaluation function, which is called the ranking technique, which is known as the mutual information or entropy-based or another types of filter feature selection. So these new types of techniques can be considered lightweight. Why is that? Because the calculation here is depending on the mathematical base rather than the machine learning or deep learning algorithm. In addition, the proposed technique can be lightweight because it consumes less resources compared to the machine and deep learning algorithm. So here we can see the methodology of a proposed step. So our methodology is composed of three main stages. The first stage is vegetable preparation. So the main aim of this stage is to prepare the data for the second stage where the lightweight feature selection algorithm has been conducted. And lastly, we have the random forest space transaction for defining the evaluating the selected features in the second stage. So as we can see here in the figure below, that the data preparation has several steps, starting by traffic aggregation, data encoding, data balancing, data scaling, and lastly the machine learning evaluation. Where the second stage contains also several steps. Start by subset generation and updating, and subset evaluation, which is clearly you can see here in the figure. in the middle that we used the regional information and chi-square algorithm. And lastly, we have a random forest, which also contains several steps from model building and training, prediction, and then evaluation measures to evaluate the model. So, in short cut, this is the content of the second stage, which is called the live feature selection algorithm. So we have in the left figure, the binary BSO algorithm is connected with a feature ranking method, as we can see here. So basically, the binary BSO algorithm starts to generate a random initial population. After that, these types of population are evaluated here using the feature ranking method, like regional information or chi-square. After that, these features will be also passed to the exploration and multiplication phase, which is the phases of the binary BSO algorithm. So after this process, or after the algorithm completed, the optimal subset of features will be passed to the next stage, which is the random forest based selective founding prediction, for building the model for training and prediction of the model, and get the result in terms of execution time and resource consumption time, and also in the data mining metrics. So here we have the design of filtered scenarios and topologies. So in this research, we investigate the performance of our detection system, as I said, against selective warning attacks. So we deploy the attacker node in different positions in the network. So as we can see here in figure A, but the attacker node in the red color cycle is near to the root node, which is in blue color node 0. So in this case, the attacker is very near to the root node, and it is important to evaluate the attacker in this position. Why is that? Because it has an important position to the root node and can have a huge effect on the network performance. After that, we evaluate the performance in figure B in the midway position with respect to the root node. And finally, we evaluate performance in far location with respect to the root node, also to see the performance of attacker node in this position. So this is the free experiment we have in this research. So this slide shows the preliminary result and expected contribution. As you can see here in the table on the left side, that the performance of the proposed technique in a free experiment, as I said in the previous slide. So as you can see here in the upper table, that we compare the performance of a standard existing meta-heuristic algorithm, which is called here the binary BSO algorithm and random forest model. And the fitness function, as we can note it here, is we have 2 times the accuracy and the mutual information, the proposed one. So in terms of accuracy, we can see overall in all experiments we have comparative result between the existing work, which is binary BSO algorithm, and the proposed technique, which is the binary BSO algorithm with the mutual information plus the random forest model. Because here we have the fitness function in the proposed technique is the mutual information. So after the algorithm evaluate and obtain the optimal solution, we also use the random forest algorithm to evaluate the optimal subset of feature, but only in the last stage. So we can see here we have 2 random forest algorithms. Here also, we can see in the term of number of selected features, we have the similar subset of features in the first table, but in the second and third table, the proposed feature selection technique or the integration of a proposed technique is better than the existing solution. It is able to reduce the number of subset of features into 17 compared to the 26 in the existing solution. On the left side, we can see here in the figure the performance of a proposed technique in terms of accuracy, position, recall, and F-measure. We can see here in terms of these metrics that the proposed solution is achieved competitive result compared to the existing solution. And so some scenarios where our proposed techniques is overcome the existing work in terms of accuracy and F-measure, as you can see here in the upper figure on the left side, that the accuracy performance is a small improvement, but also we have in the F-measure metrics. In addition, on the left side figure, we have also an improvement in terms of precision, and on the right side we have improvement on the accuracy, performance, and precision also result. So despite of this small improvement in terms of various metrics, we have a major improvement in the term of number of selected features, and also we expected that the execution time of BSO algorithm will be improved. Why is that? Because the proposed techniques is faster than the existing techniques, which is the machine learning algorithm. Because as I said, it's evaluate a subset of features based on number of mathematical model rather than machine learning algorithm, which is needed training and prediction technique. So, as a conclusion, we can conclude that the obtained result that proposed techniques is overcome the existing solution in terms of number of selected features and in terms of various metrics like the accuracy, precision, recall, and measure. Also, we expected that after the evaluation, because it is still an ongoing research, that we will compute the time execution time performance, and we expected that we will get a better result in terms of execution time and also in terms of CPU and power resource consumption, which makes this proposed techniques is compatible with the resource constraint in the IoT environment. And also we notice that in the term of number of selected features, that proposed techniques is aimed to reduce the number of selected features to 21, 17, and 15 features in the scenarios. So we can also conclude that the proposed techniques is feasible to be used in IoT scenarios, and we get impressive results from that. And we also extend this work to identify other types of IoT networks attacks like flooding, rank attack, and cyber attack. Also, we can investigate and extend this work to investigate other types of RPL topologies to identify the attacks from different types of IoT application. Thank you so much.
Excellent. Thank you very much for that presentation. Did anyone in the room or over Zoom have any questions for the presenter? Not for me.
Yes, I have a question.
Yes.
Regarding the feature selection, is it the proposed approach selected the features like giving fixed number, or the algorithm is selecting dynamically?
Okay, thank you for your question. Regarding the feature selection, here the selection of the features is iterated, repeated, and selectively. I mean, the selection of the features is depend on the performance of the BSO algorithm with the proposed rank technique. So it will select different types of features and evaluate each subset of features individually. Then the algorithm will decide which set of features is optimal based on the performance of the random forest algorithm. So the subset of features that attain the higher accuracy will be selected from the list of this solution generated by BSO algorithm. So it's different compared to the standard feature selection algorithms like the ranking techniques or filter feature selection, like the entropy-based or unusual information, which is select only one type of features and evaluate this subset of features using machine learning evaluation.
Okay, thank you. For detection, you are using only random forest, is it?
Yes.
Okay.
Okay, why we use random forest here? Because during the first stage, if you see here in the methodology, we tested, if you can see here in the figure, we tested different types of machine learning algorithm, and based on the result, we selected random forest algorithm to evaluate a subset of features in the second stage. So it's based on its performance.
Okay, thank you for informative information. Thank you.
Welcome.
Is there any other questions for the presenter at this time? Excellent, thank you. Can you just go to your last slide just for your email address, just in case anybody else wishes to reach out to you directly for comments or questions about your work? Excellent. Thank you very much for that. We'll move on to speaker and presentation number 2, Abdullah Ahmad Omar Bahashwan, sorry. Bahashwan's presentation on high and low rate data set-based DDoS attacks against software-defined networks. So I'll hand it over for your presentation. Mr. Bahashwan, you there?
Yes, I'm there. You hear me?
Yes, we can hear you now. Thank you.
Okay. Good morning, everyone, and thank you all for being here today at APAN58 Security Working Group. My name is Abdullah Ahmed. I appreciate the opportunity to present my work on high rate and low rate dataset-based DDoS attack against SDN, and share the insights and contribution I have gained through this process. Without any further delay, I'm going to start with the introduction. Nowadays, the traditional network suffering from many issues in terms of management, security, and other essential aspects. For this reason, new technology has shown up to enable higher management and giving more flexibility. This technology is known as software-defined networking controller. The SDN is a new networking architecture that separates the control plane and data plane. This innovative technology is designing for next generation networks that have been repeatedly highlighted with the open flow protocol. The SDN is a central controller that manages the whole network flow with the minimum efforts, makes the network more scalable and agile. As can be seen, this figure illustrates the difference between the SDN network architecture and traditional network architecture. The SDN networking architecture consists of 3 layers. First, the application layer consists of application programs that are implemented over the control plane and communicating with the SDN controller through the northbound API interface. Second, the control layer that contains the SDN controller to rule the entire network functionality. This is the last data plane layer that consists of the SDN switches or devices and communicate with the SDN using southbound API interface. The SDN architecture became broadly adapted in new emerging technologies such as cloud computing, IoT technologies. However, several security challenges appear to disturb the SDN network normal operation. The SDN network has no security defense by default, which exposes the SDN controller to the most common attacks of these days, like high rate and low rate DDoS attacks. In recent years, there has been significant increase in the use of deep learning approaches to address the requirement for developing powerful detection systems. One significant advantage of deep learning over traditional machine learning is the superior performance in analyzing large-scale datasets. Additionally, deep learning has gained popularity in detecting SDN DDoS attacks flooding due to its ability to learn the complex patterns associated with these source attacks. This slide discusses the relevant works on deep learning-based approaches that utilizing for detecting SDN DDoS attacks. As presented in this table, these approaches having some limitations. One of these limitations, most of these approaches primarily focusing on detecting high-rate DDoS attacks, which are easy to detect due to the massive spoofed traffic against the SDN network. The evaluation of these approaches frequently employ unrealistic datasets that do not accurately present the characteristics of the SDN network architecture, since the structure of the SDN network is totally different from the traditional network. Some of these approaches exhibited inadequate performance when it comes to detect standard or conventional DDoS attacks. Moreover, none of the existing approaches attempts to detect low-rate DDoS flooding attack. So in this type of attacks, the attacker sent low-rate spoofed traffic, which is similar to regular traffic, since both having the same characteristics as legitimate traffic. Due to these difficulties, The existing approach is just concentrated on standard or conventional DDoS flagging attacks and does not consider both simultaneously. Additionally, this table presents the SDN datasets that having some limitations. Most of these datasets containing several traffic features, even though some contributed datasets having quite a few features. Most contributed datasets are limited to conventional DDoS attacks, except only these datasets. However, this dataset is limited only to UDP. DDoS attacks has limited traffic features and not publicly available. So this figure presents an overall methodology for the proposed SDN datasets and the deep MLB detection approach, which consists of 5 stages. The first stage is about generation and capturing stage, aims to propose a realistic SDN dataset. The second stage is about network traffic feature extractions, where a set of statistic features are deriving from the SDN network traffic flow. The third stage involves construction and pre-processing, preparing the datasets for the proposed detection approach to yielding meaningful results and significant results. The fourth stage involves dataset validation, conducted to ensure that the proposed dataset meets the requirement to serve as a benchmark dataset for this research and research community. The fifth stage is about deep learning MLB detection approach. Is training on the proposed datasets to enable effective detections of both high rate and low rate DDoS attacks. This figure illustrates the virtual testbed network topology for creating the proposed dataset. Mininet is considering to create the realistic virtual SDN network. The testbed feature a linear topology designing as the following: one OpenFlow one box controller acts as the root node and function as the network brain of the entire SDN network. One OpenFlow switches is acting as a gateway that connects the controller and the data link layer. The testbed consists of 64 nodes from 1 to 64. There are nodes act as attackers to generate high rate and low rate DDoS attacks against the SDN controller by targeting victim nodes. The remaining nodes generated normal traffic and act as a legitimate node. The proposed dataset considers 6 relevant scenarios. The reasoning behind that is to evaluate the effectiveness and consistency of the SDN security approaches in detecting 3 types of classes of DDoS attacks with different traffic variation rates. In this stage, the inbound and outbound network traffic are captured. The traffic is captured either from the SDN controller in the case of DDoS attacks or from the switches in the case of normal traffic. This step includes all SDN network traffic, both inbound and outbound. However, it's crucial to filter out relevant traffic to create datasets and save it as a backup file for further processing. This stage also involves transforming raw data into more suitable format. We utilize the CIC flow meter feature extraction method, recognizing for its ability to extract network traffic features. The output of this step, a collection of statistic feature extracted from the SDN network flows. Each feature carries a distance, meaning serving as an indicator of normal or abnormal flow. The reason or the rationale behind employing CIC flow meter is that it serves as a validated feature extraction method. It's used to extract different range of statistic features. Additionally, it's provide a more comprehensive and representative set of influential features. Also, finally, the dataset containing these features can be categorized as a flow-based dataset. The third stage involves construction and pre-processing. The dataset by labeling, transforming, balancing to ensure equal distributed of label classes, normalizing the dataset features within a range 0 to 1. This step enhances the dataset quality and reliability and preparing it for the proposed detection approach to yielding meaningful and significant results. In this stage, the datasets undergo validations before being accessible to the research community. This stage aims to ensure that the generated datasets are applicable and fill all the requirements to serve as a benchmark dataset. These requirements including realistic traffic, diversity of DDoS attacks and scenarios, datasets completeness, labeling, sufficient traffic size, balancing traffic classes, representative features, and detection accuracy verification. This table provides an overall of the distributed of these dataset samples for both multi-class and binary class classification. At this stage, the dataset samples are applied to the proposed deep learning multi-layer perceptron detection approach. Two testing techniques are considered for assessing the detection approach generalization. First, the split test technique divided the dataset into sufficient large portions of datasets like 80 for training set to enable the model to learn diverse patterns, and 20 is reserved for testing set for evaluating the model performance on unseen dataset. The second is the cross-validation technique. This technique is critical for mid-evaluation as it involves training and testing on different subset of overall, considering both techniques results in a more robustness approach performance assessment compared to solely relying on the split test technique. The following slide is about experiment results and discussion. This slide is about results and discussion. A realistic dataset has been generated to meet the requirement for serving as a benchmark dataset. Additionally, the proposed dataset underwent qualitative comparison with the existing SDN datasets and quantitative evaluation across all 8 scenarios to highlight its superiority. Based on the literature, these criteria has been formulated for qualitative comparison between the proposed dataset and the existing ones. So the candidated dataset must be realistic. Total number of instances up to 1 million. The dataset must include variety of attacks and scenarios. The dataset must be labeled, completed. The dataset must include sufficient number of features for allowing the researchers to understand more about the attacks patterns. The dataset must be verified in terms of detection accuracy. Finally, the dataset must be publicly available. As shown in this table, most of these datasets fails to include up to 1 million. Additionally, most of them fail to include both high rate and low rate DDoS attacks. The only exception dataset is this one. However, this dataset is limited only to UDP DDoS attacks and does not consider a variety of attacks. Some of the existing datasets are incomplete, having some columns are missing. Some of the datasets having insufficient number of features which are necessary for the researchers to understand more about the attacks patterns. Also, all the existing datasets have been verified at least in terms of detection accuracy, and most of them are publicly available. In summary, the proposed dataset addresses the limitation of the existing SDN datasets by considering a variety of attack scenarios. Also, the proposed datasets meets the requirement to serve as a benchmark datasets, include sufficient number of features. Overall, the proposed dataset is publicly available. The proposed detection approach also has been quantitatively evaluated using 8 scenarios as presented in this table. The comprehensive evaluations try to cover all possible attack scenarios, including both binary and multi-class classification. It includes evaluation metrics such as detection accuracy, precision scores, recalls for each individual classes. Based on the literature, these metrics are commonly used for evaluating individual classes. The finding in this table demonstrates that the proposed approach achieves good results across all attacks and scenarios. Moreover, the proposed approach has been quantitatively evaluated in terms of average performance. The proposed approach achieves high detection accuracy, precision, recalls. On the other hand, the proposed approach achieves low false positive, false negative, and true negative, while the classification error is minimum. These results observed from different type of DDoS attacks against the SDN controller. Conclusion, this paper introduces the HLDD DDoS SDN datasets to address the key challenges in the SDN domain. This dataset simulates the prevalent DDoS flooding attacks with a variety traffic rates by meeting benchmark criteria for size, stack diversity, and features. Also proposing anomaly-based detection approach for training and evaluating the datasets. The experiment results demonstrates that the detection approach exhibited good performance in detecting these attacks. For limitation, it's important to note that the proposed datasets were intentionally generated with a virtual SDN environment, addressing privacy concerns, enable control over the severity of DDoS attacks. However, this virtual setting may not fully capturing all network flows, such as variety, traffic, network size, application types. The dataset scope is specifically related to TCP, UDP, ICMP, DDoS attacks. Also accommodating fluctuated in traffic rates. From practical perspectives, the proposed dataset serves as a control testing ground truth environment for the new SDN detection approaches. This approach allows for identifications of the strengths, weaknesses before implementation in a real-world network. So the proposed dataset stands as a valuable resource for the researchers, practitioners in the field of the SDN DDoS attacks. The future work, I focus on enhancing the detection approaches through the implementation of efficient sample feature selection technique. This approach aims to reduce the dataset dimensionality, ultimately boosting the performance and generalization of the detection approach. Also minimizing the false positive and classification error. This is the article source of the proposed dataset, validating the theoretical framework and methodologies employed in this benchmark dataset. For more details, you may access this article directly. Okay, thank you.
Thank you very much, Mr. Bahashwan, for that great presentation. Is there any questions in the room?
Which criteria or techniques that you have used to validate the data sets? Is there any comparison?
Which slide?
It may be data validation slide.
You mean which criteria?
Yes.
Yes, okay. Yeah, this one based on the existing related works, we formulate these criteria. This criteria has been formulated based on the existing works. We have coming out with these criteria.
Maybe just to expand on that, was that criteria related to the table that you displayed on another slide that showed?
This one?
No, it was the larger table that talked about whether it had the high or low, the number.
This one?
No. I can't remember which slide it was. It was a very, very large table.
This one.
No, keep going. Yeah, no,
This one.
that might have been the one, yeah. Was that listing how it was validated, looking to make sure that it satisfies all those feature sets?
Yes,
Or
this one criteria has been formulated based on the related works.
Yeah.
Also based on the existing SDN datasets. As can be seen, some datasets having less number of features, which is not efficient, not enough for the researchers to understand more about the network, the attacks patterns. Datasets having incompleted columns. Some datasets, they are focusing just on standard or conventional DDoS attacks. Some datasets, they have less number of instances, which is not sufficient for deep learning. All these limitations. So we came up with these criteria. Is it clear?
Yes, yes, thank you very much.
Thank you.
Other questions? Oh, yes, sir.
Thank you for a very nice presentation. Perhaps I missed something regarding the high and low data rate.
Okay.
My first question is, what is the high data rate and what is the low data rate? I mean, how you defined it in your research. And the second question is, what is the impact of high and low data rates?
In high rate data, the DDoS attack, the attacker is send a massive or spoofed traffic against the victim node. Okay? But in low rate, the attacker is send a slow malicious traffic against the victim, against the victim node that affects the SDN controller by the time, not immediately. The impact of high rate is, we can say it, immediate, but at low rate it takes some time. That's the major difference between them.
Yes, thank you for that response.
Thank you.
Is there any other questions either on Zoom or within the room?
Okay.
Just see, is there any questions in Zoom as well?
Hello. I have one
Yes.
question about the size of the data set you proposed. Actually, in this table, I think there should be one column related to the size, because size makes a big difference in the results also.
The size here, can see axis.
Any other questions? Excellent. I think that is all for the questions. Thank you again for your presentation, Mr. Bahashwan. And
Okay.
we'll move on to the third presentation. Third presentation is from Mithiran Parathban, sorry about the name butchering here, presenting on MALBED, enhancing peer-to-peer botnet detection with specialized test bed. So I'll hand it over for your presentation, sir.
Good day everyone, my name is Mitran Patiban, and today I'll be presenting a title called MALBED, Enhancing P2P Botnet Detection with a Specialized Test Bed. And I'm doing my Masters in National Advanced IPv6 Center in University of Science Malaysia. So this will be the agenda for today, where I'll be giving a brief introduction to the topic, and I'll be moving on to botnets, the different type of botnets and how they interact with each other, followed by problem statement, monitoring mechanisms, and finally I'll be concluding the presentation. So as we all know, the cyber attacks trend globally is going up, and this is due to many reasons, and one core reason is malware, where in 22nd July 2024, a malware called Golish exploited a research center where they are used as devices to conduct research projects. And in United States, officials found 19 million infected computers that enable identity theft and also child exploitation. And 19 million devices were found globally, not just in the United States. And also in the start of this year, researchers uncovered the major surge in global botnet activities. Botnets have caused millions of damages or even billions of damages, and in 2024, as of now, $30 billion $30 billion damages are caused by botnets alone. And I would like to highlight this graph here, where it shows Mirai botnets targeted Asian hosting providers with 2 TB per second DDoS attack. And I say variants of Mirai botnets because Mirai botnet source code has been made public, and there are many variants of Mirai botnets. So I've been talking a lot about botnets in the past 2 slides. So what is a botnet? It's a network of comprised devices controlled remotely by an attacker. Botnets are used to perform malicious activities like DDoS attacks, sending spam, or even spreading malwares. Botnets pose a widespread threat because they consist of millions of devices across the globe. There are 3 different types of botnets. The first one is a centralized botnet, where it's controlled through a central C2 server where all bots receive instructions from the bot master. And the second one is the decentralized version of it, where it's similar to a centralized architecture, but it uses multiple redundant C2 servers. C2 meaning command and control servers. And finally, the most interesting part is the peer-to-peer botnets, where each bot acts as a client and a server communicating directly with each other. So I would like to highlight 2 types of botnets. The first one is centralized, and second one is peer-to-peer. And as I mentioned, centralized botnets are botnets that uses a centralized C2 server, and the bots regularly poll to the C2 servers for updates from the bot master and apply them immediately. This architecture is easy to deploy and has low communication latencies, but it has a major disadvantage where it has a single point of failure, and the entire botnet becomes inoperative if the C2 server is removed, and defenders can easily track and enumerate all infected machines. The second one is the peer-to-peer architecture, where it eliminates the vulnerabilities associated with centralized architecture by avoiding the single point of failure seen in the centralized system. And the network can continue to operate even if the individual bots are taken down, as commands can be injected to any bots, which allows multiple entries for the bot master to inject their commands, making it harder to trace the bot master. Given the growing complexity of peer-to-peer botnets, traditional methods are insufficient for effective analysis. Primarily, there are 2 types of monitoring approaches for peer-to-peer botnets. The first one is in the wild, the second one is test-bed. So the main differences between the in the wild analysis and also test-bed analysis, where in the wild analysis, the tracking activities of known botnets are currently active in their natural habitat, meaning the analysis is done using real-life botnets that are currently present globally. But it comes to a risk where operators, if they detect that they are being monitored, they potentially trigger attacks to show retaliation. Whereas in testbed analysis, emulation experiments are conducted using machines and infrastructures within a laboratory. It empowers comprehensive investigation across diverse parameters and gives unwilling insight. So the problem statement for this topic is, ideally we want a controlled and secure environment to analyze the behaviors and vulnerabilities of peer-to-peer botnets. However, the decentralized nature of peer-to-peer botnets and the need to prevent any risk to actual network infrastructure complicate the study of peer-to-peer botnets. As a result, researchers face challenges in developing effective mitigation strategies, potentially leading to incomplete understanding and insufficient defenses against peer-to-peer botnets. So I've mentioned that monitoring mechanism is a crucial part in analyzing a peer-to-peer botnet, and in terms of monitoring mechanism in peer-to-peer botnets, it involves analyzing network traffic to detect command dissemination and cataloging infected devices to understand the botnet scale and structure. To enhance these monitoring efforts, a dedicated testbed serves as a primary environment, providing a controlled and secure platform to safely deploy, study, and refine monitoring mechanisms for deeper insight into the peer-to-peer botnet architecture. So as I mentioned in the previous slides, testbed analysis is crucial for peer-to-peer botnets, but what are the features that is needed within testbed to have an effective analysis? We have done our research and we have seen to related works, and we have come up with 5 features that are crucial to have in any testbeds for effective peer-to-peer botnet analysis. The first one is security, followed by fidelity, scalability, automation, and finally reproducibility. So let us look into each of these features for better understanding. And services like DNS and HTTP and other crucial services should be replicated within the testbed for authentic botnet behaviors. Third one is scalability, and as we all know, the testbed should be able to support large-scale replication of nodes and networks, and the testbed should be designed to easily scale up or scale down depending on the number of nodes within the topology, and depends on the peer-to-peer botnet's requirements as well. Automated deployment and configuration of nodes to reduce manual intervention, where structured configuration files automate and manage the testbed infrastructure. And also the automation should be able to modify the malware execution and also test during the analysis for a better understanding of peer-to-peer botnet. And finally is reproducibility, where it requires a thorough documentation of network topology and configuration to ensure experiments can be replicated. The testbed should use version controls for configuration and scripts, ensuring that changes can be tracked and experiments can be repeated under consistent conditions. So I'd like to conclude today's presentation by highlighting what we have covered so far. The first one is we have highlighted the problem caused by malware, especially botnets. We have also reviewed the different types of botnets and what botnets are. And we have seen the different types of peer-to-peer botnet analysis. And finally, we have reviewed the features needed for a test bed for a peer-to-peer botnet analysis. And I also like to mention that this is a very high-level presentation, and currently we have a work in progress for the deploying the test bed as well.
Excellent. Thank you very much for that presentation. Do we have any questions in the room or remote over Zoom for this presenter? No, I think you displayed everything very clearly in your presentation, so we don't have any questions at this time. Might just leave your slide up just for another second or two if anyone wants your email address or contact details, but thank you very much for that presentation. Excellent. Well, that concludes the 3 presentations for the Security Working Group for APAN58. Thank you very much to all of our presenters and to the co-chairs for their work. The next conference will be APAN59, which is going to be held in Tokyo. So we'll do a call for papers out through NRENs and various organizations to see if there's any interests from various organizations for next year. But please keep an eye out for that email when it comes out. We're finishing just a few minutes early before break time, but thank you very much for everyone who's attended, both remotely over Zoom as well as for those that are in the room for this session. Thank you very much, and we will see you on email before the next APAN meeting. Thank you very much, everyone.